So for today's lecture, we're going to be talking about linear regression. And linear regression at its most basic form is very similar to correlation. It's going to use a lot of the same concepts. However, it needs to be differentiated from correlation, both statistically, in other words, what letter we use to represent it. So we're not going to use small r, but it also adds something to correlation. So if you run a linear regression on the same data that you could run a correlation on, you're going to find the same statistical significance and the same effect size. The actual test statistic may be different because we are actually doing a different equation. And what that equation is doing is it allows us to do a prediction with correlation. So correlation just looks at the relationship between two variables. Linear regression looks at that same relationship, but adds a further layer. It adds the ability to predict based on that study in future populations. So for example, if in our sample, our correlation showed that there was a relationship between anxiety and depression, two measures that we've measured, we can theoretically define which one is first and which one is second. That's irrelevant to this example. So we know there's a correlation. There's a significant relationship. As depression increases, so does anxiety. With linear regression, we would get that same information, but we would also get additional information allowing us to predict someone's depression based on their current level of anxiety in a new population. So in other words, linear regression is based on the idea of doing prediction across external validity. We are using study data, we're using the statistics that we found in a sample to make future predictions based on that sample. And we do this a lot in regular job work. So for example, if you've taken the ACT or SAT to get into college, those tests are based on previous correlations to allow linear regression. When you provide a university with your SAT score, it allows them to predict how good of a college student you're going to be. So for example, we're now using the relationships that have been found in the past between, for example, the SAT and college GPA to predict in the future, based on your current SAT score, what will your performance in college be like? Now, like all prediction in psychology, it is not perfect. There is error. There are always going to be people that score low on a test that actually excel for various reasons in college. And there's going to be people that score very highly on the test that for various reasons do poorly in college. But most people, on average, I often like the term better than Vegas odds. Most people, the higher they score on that predictor test, the better they're going to do in college. So that's what linear regression is adding. It is giving us the same information as correlation, and it is adding prediction. Now, an additional effect of regression is, as we are going to discuss, at least briefly in this class, you can also do more with regression than you can with correlation. Correlation is fairly limited in what exactly you can actually look at as far as research questions. It basically looks for the relationship between two continuous variables, or a continuous variable and a dichotomous variable, depending on how it's coded. That's really all you can do with it. With regression, this is the first step into a much broader set of statistics that allow us to look at much more complex relationships. But for the purposes of these slides, we're going to be looking at linear regression simply as the same requirements as correlation, but adding that level of prediction. So going back to the definition of a correlation measures the association between two variables. It can estimate whether and to what accuracy you can predict the scores, but it doesn't actually give you the ability to predict. So we cannot actually use a correlation to directly predict a score on one variable, the outcome, from another score on the predictor. So generally speaking, though correlation, the statistical technique, is pretty much dumb to what the variables are. It's simply looking for a relationship between two variables. Theoretically, it is important for us to know what is our outcome and predictor variable. Outcome is a way to think of as a dependent variable. It's what we're expecting to be impacted. And the predictor variable is often our independent variable, if you're thinking about it experimentally. So these are two different terms, but basically it means that the predictor is the variable that we would use to predict future behavior if we could, and the outcome is the variable that we'd want to predict. So outcome and predictor are determined by past research, logic, and they can be somewhat arbitrary. For example, depression and anxiety have a fair amount of back and forth relationship. You can increase anxiety, and that often will impact depression, and you can impact depression, which will often impact anxiety. So regression analysis is, again, a measure of association between those two variables, the same as correlation. But it also can be used to estimate whether and to what accuracy we can predict a score from one variable, the outcome, on the score of another, the predictor. Predictor is chosen based on availability and temporal precedence to the outcome. So generally speaking, at this point, unlike a correlation where it might be arbitrary, if we're doing a regression analysis, we need to have theory and logic backing up what is our predictor and our outcome. And the predictor is often going to be something that we would have access to before we have the outcome. A lot of employment tests use this. For example, they might be measuring your cognitive ability. That would be a predictor of performance. Once you have the job, that would be the outcome. So we're going to be using regression to predict a score on one variable, the outcome, from the score on another. And again, it's important to recognize that though the analysis doesn't know what we're doing, we're also generalizing from our sample. So we do need an actual sample where we have both the outcome and the predictor. We look for that relationship, and then we get the information of how to do the prediction. The prediction is going to be done on other people, other samples, where we don't have that outcome variable yet. And therefore, we have to be really conscious in our methodology, not our statistics, of how we're generalizing this information. Now, as I said, regression analysis also opens the door to a much larger toolkit of opportunities, including the ability to look at multiple variables at once. In other words, multiple predictors on a single outcome. And this is usually referred to as multiple regression, which we'll at least discuss a bit in these various lectures, but we're not going to actually get into the analysis of. So prediction. We can use the regression to predict a score on our dependent variable, the outcome variable, from a score on our independent variable, the predictor variable. And we do this by using the line of best fit, the regression line. And this is basically a way to think of the regression line is that it is a line that is the average of the smallest differences between every point on a scatter plot. So for example, here's two examples of scatter plots. And remember, a scatter plot is simply we're just charting each person's score on both variables. So here we have GRE and GPA on the first chart to the left. And we have their GRE scores and their GPA. And we'll notice that each dot represents one particular person in our sample. So if we go to the very top right, we see someone who had a 4-point GPA and a GRE score of approximately 750. If we go all the way to the bottom left, we see someone that had a 300 on the GRE and a GPA of 1.0. Notice that very few people are actually on that line of best fit. That line of best fit is the best line, best fitting line that we can draw that minimizes the error of each point to the distance of the line. In other words, if we drew any other line through this data, we would find greater differences on the average. So we're basically mathematically looking to see what is the line that fits this data the best. On the example to the right, we see a much tighter relationship. This is an example of, this is actually from behavioral research, and it's looking at temperature versus running speed. And this is a negative correlation. As the temperature goes down, running speed goes down as well. So as one goes down, the other one goes down. So in this case, we find at the top left, we find someone that was at a temperature of negative 850 and had a running time of 4.0. And at the very bottom, at the bottom right, we find someone that was at a temperature of approximately negative 270 that had a running speed of 1.0. Now notice that this data is much more closely associated with that line of best fit. Not every single data point's on it, but a few of them are, 3 of them I believe, and most of them are fairly close. This also tells you that the stronger the relationship, the better the prediction. So for instance, if I was looking at the data on the left and I made a prediction based on the line of best fit of someone that had a GRE of 600. If we look at the 600 at the bottom there and take it up to the line of best fit, we'd see that we'd predict a GPA of approximately 3.0. However, if we look at the actual data, for example, a GPA of 500, the prediction would be a GRE of 500. The prediction of the GPA would be about 2.5. What we actually found in our data set was a GPA of 4, a GPA of 3, and a GPA of 1. So again, there is going to be some error. However, if I was looking at that temperature gauge, So again, if I have someone at a temperature of point or -40, we'd predict a running time of 2.0. What we actually find is that there was only one person that actually scored in that range, and that person was right on that line of best fit. There's two other people that had a running time of 2.0. One of them was at a temperature of approximately -450. The other one was at a temperature of approximately 350. So again, we're seeing less variance in our prediction. So the greater the association between the two variables, the stronger the relationship is, the larger the correlation. If we were running a correlation, that would be R. If we're running a regression, it's represented by the Greek letter beta, capital. So notice that's how we let people know which statistical technique we used. We'd still want to, in a results section in an APA paper, tell them what statistic we did. But if you actually understand statistical notation, sorry, you would actually know just by looking at the actual stat line. Ah, it's a beta, they ran a regression. Or it's a lowercase r, they ran a correlation. So this also means that the stronger the correlation, the stronger the prediction. So in the case of a correlation, we're going to get more information than just that beta, that test statistic. We're also going to get a b and a y prime. And these are basically information about how to do the prediction. The larger the shared variance, so the effect size. The effect size is the same, generally speaking. Now, as we get into multiple regression, where we have multiple variables, we are going to find different effect size types. But in this case, we should find the same effect size if we're running a correlation or regression on two variables. And that effect size is still r squared. And the stronger that relationship, the larger the test statistic, the stronger the shared variance, the better the line of best fit represents the data, which means the more accurate our prediction is of the outcome on the predictor. So again, just an example here, we have our outcome, and we already looked at this data. This is GRE versus GPA, and this is a moderate relationship. If we actually take a look at it, we're going to see that there is a data point here where someone was as predicted. They're on the line. They had a GRE of about 350 and a GPA of 2.0, which is what we'd predict in a future population. This person is not quite as accurate. So again, if they had a GRE of approximately 450, we'd expect their GPA to be about 1.75, maybe 2.0, maybe a little over 2.0. It actually is a little bit lower than that. So if we were actually trying to predict this person, we'd be a little bit off. This person, we'd be way off. So someone with a GRE of 300, we'd anticipate a GPA of about 1.5. This person actually had a GPA of 4.0. And that's one of the reasons we're going to look at that effect size, that r squared. This particular data set would probably have a relatively small r squared. For example, maybe 10% of the variance explained. Still significant, still usable, but it also means that about 90% of what's going on is being explained by other variables. So this person may have scored poorly on the GRE, but they may put a lot of extra study time in. They may have a lot of support from their family. They may have been raised in a home that really valued education. We're not sure what's driving this person, but we know that beyond their ability, which is what the GRE is meant to measure, there's other predictors that are actually going into there. Our y prime at 500, and y prime as our predicted score, is 2.5, for instance. So that's what we'd actually predict. Y prime, whenever we see y with that little apostrophe after it, that means y prime. And that is our predicted score. So again, if we look at that, we can also see that there's quite a few people that did not score what we'd expect them to score. So again, when we're looking at this, we're actually kind of trying to graph out where individual points are. So here our y prime is 2.0, and what we actually get, the actual score would have been 2.0. So that's perfect prediction. Here, our y prime is 2.5, but the actual y's we got was 1, 3, and 4. So there's definitely error at that point. We can tell that we can make a prediction, and all things being equal, it'd be better than just guessing what someone with a 500 GRE would have, but it's not always going to be perfectly accurate. So the error in prediction is often referred to as simply y minus y prime. So for instance, the error for someone with a 3.0, so their y is 3 minus 2.5, is basically 0.5. The error between someone with a y of 1 and 2.5, that's y 1 minus 2.5, is an error of negative 1.5. And likewise, the y prime for 4.0, again, y is 4, y prime is 2.5. The error is 1.5. It was 1.5 off from what was actually found. So that's how we're looking at prediction. We're using this information to make predictions on future scores. And you can tell they're not going to necessarily be as accurate as we had hoped, but it also increases the stronger the relationship is. Once we have y prime, we're also going to be looking at notice that there is, and this is why equal interval is important, there is an equal amount of change no matter where we are on that line. So every time we see a 1-unit increase in GRE, in this case 100 points, we're finding an equal increase in GPA. So for each increase in our predictor variable, we find an equal increase in our outcome variable. Now, if there was a negative relationship, we'd find the opposite. It would be going down at that point. So 1-unit change in predictor equals how much change we actually find in the outcome, y. So let's look at this prediction again, positive or negative. We find the same result when we're looking at prediction. We're going to find the same process. And again, in this case, we can see we have this perfect prediction. We predicted a y prime of 2.0, and what we actually found was a y of 2.0, which means error is 0. In this case, our y prime is 3.5. Our actual y was 3, for example, the one below the line. So this would be an error of 0.5 or negative 0.5. And finally, we also have a 4, and that'd be a positive correlation of plus 0.5. So hopefully this is kind of giving you an idea of how we can actually use the calculation of the line of best fit to predict future scores. And again, we're going to find that even that negative relationship, we're going to find that same effect of for 1-unit change, we find 1-unit change or one amount of change in y, and that's always going to be consistent. That's one of the reasons we're drawing this linear line, this line of best fit, to allow us to do simple prediction. That's also why it's important that when we're looking at regression, we want to make sure that we actually have linear relationships. So for instance, if we actually find a statistically significant effect, but we look at the scatter plot and we find that the data really doesn't follow a linear pattern, then it may be inappropriate to do prediction.